Welcome back to Caesar Education. Today we are talking about uniform motions under the chapter of kinematics in one dimension. Now, when we talk about uniform motion, we are talking about a motion that is moving steady. Now, suppose that we draw a motion diagram and say that subject A was at this position at 0 seconds. And then we followed him and found out that after 1 second, he was 2 meters away. Now, if we draw 2 meters away and say he was 2 meters away after 2 seconds. Now, after 1 second, and then after 3 seconds, he's right here again. After 2 seconds, he's there again, and we draw his vector, his displacement. Now, with this, I'm showing his displacement. Now remember, displacement is position, is a change of position and direction, because displacement is a vector, so it has a magnitude and a direction. So if I show this that he moved to the left 2 meters, that means I'm showing his displacement and not just position. Now he moves another 2 meters in 2 seconds. And then he keeps moving and moving and moving steady like that. For every second that he moves, we found out that he moved for 2 meters. So I draw displacement 2 meters, 2 meters, and 2 meters. Now it shows that for every second that this person moves, they move 2 meters. Now this is uniform motion because the displacement between each motion is equal. So the displacement vectors are equal in this case. So we can conclude that the motion is uniform. So how do we define uniform motion? Uniform motion is motion in which whatever is moving, it does not have any acceleration. It moves at constant speed, and it does not have any acceleration. Now, uniform motion is motion whereby your item is moving at constant speed with no acceleration. And by no acceleration, we means that for every second it gets displaced an equal amount. You see there, for each second it moved for 2 meters, 2 meters, 2 meters until it got to 5 seconds. We are saying that uniform motion, it is motion in a straight line, with unvarying speed. Now, to represent displacement over time graphically, we call this a position versus time graph. When we change displacement over time graphically and we show it graphically, we call this a position versus time. A lot of people will just say it is a x versus t graph. So it will tell us where a person was at a certain time, and then it will also show us where it is after a certain amount of time. And we can drag that motion using a position versus time graph. Now let's plot this motion of a particle moving at 2 meters for every second. Now at 0 second here at the beginning, that means this is our initial position. It was at 0 because it hasn't moved in 0 seconds. We cannot measure something when time hasn't moved. So it hasn't moved, so it is at 0. Now after 1 second, our particle has been displaced 2 meters. Now we plot it. Here you can see I wrote the x, and the x will show us our position, and t is for time. Now after 1 second, time is in second, position is in meters. After 1 second, we are at 2 meters. After 2 seconds, we have moved 2 meters and 2 meters. So after 2 seconds, we are at 4 meters. Move another 2 meters. At 3 seconds, it seems we have moved 6 meters. So we keep going. At 5 seconds, we have moved 2, 4, 6, 8, 10. After 4 seconds, we have moved 8, and at 5 seconds, we have moved 10 meters. Now, what I want you to notice is that since this is uniform motion, the position versus time graph, it will follow a nice straight line. That's why I went to the trouble of trying to create a coordinate system here to show that uniform motion will form a straight position versus time graph, and will have a nice linear graph like this. And that's only for uniform motion. We can actually amend and make the definition of our uniform motion even better and say uniform motion is a type of motion where the position versus time graph is a straight line. Now you have all this way that you can define your uniform motion. And the second thing that we can take from it is we can see how fast our particle was moving, how fast our object was moving. Now, from this motion diagram, we can see that for every second, it moved 2 meters. 1 second, it had moved 2 meters. 2 seconds, it had moved 4. 3 seconds, it has moved 6 meters. So it shows us that our particle was moving at a speed or velocity of 2 meters per second. So it was moving 2 meters per second. And from this graph, you can see that this is presented by the slope of the graph. Now, if you take this small part, you can see that it moved 2 meters for 1 second. If you take this part, you can see that it moved 2 meters from here to here in 1 second. So the slope of the position time graph gives us its speed or velocity. Now, how do we actually calculate it? If we know that the slope of the graph is the speed or the velocity, how would one go by calculating it? So what you would do is that you would take, like I did here, you see that we said 2 meters moved in 1 second. To find our average velocity, we would take a change of x, which is the change in y-axis. In this instant, position is presented by x, but it is in the y-axis. I hope you see that distinction there. So we would take the change in x, which is this change. Let me take a nice color and say which is this change, and then divide that by the change in time, so the time interval. So here we have a change in position over the time interval if we want to calculate the velocity. Now we say that this is our change in position and this is our time interval, and that gives us the slope of the graph, therefore giving us the speed or the velocity. To expand here, we're basically just saying take the x here at the final, subtract it with the x at the initial, and then divide that by how many times it took you to move that amount of position. Now our x will be used to represent time. Hence we say change in x over time interval, the time it took to move that amount of position. Here we say it takes 1 second to move 2 meters. Hence our speed, our velocity, we said it was 2 meters per second. No matter how big your chunk that you take, it will still give you the same answer. Even if I only took this little block here and say changing x over time interval, it will give you the same time because the slope on the straight line is constant throughout. And that's what the point we are making, that the motion will be uniform throughout. Now, can we actually find the function of the velocity over time, the speed over time, from just looking at the graph of position over time? Now, I have a nice graph here that is showing a motion of a particle over time. We represent x in the y-axis and have t. X is giving us our position in meters, and time is giving us our time in t is giving us time in seconds. The same thing that we're gonna have down here and say that we have t in seconds, but now we want to find the velocity, and our velocity is represented by v, and it is given by meters per second. So what we are going to do now is, we just said that to find the velocity we must look at the slope of our position versus time graph, and then that slope gives us our velocity or our speed. But now we're gonna be more specific and see how velocity, why I keep exchanging speed and velocity. It is because in this instant our speed is just a magnitude, so we know that it is 2 meters per second. But how can we use this to know which direction it is actually going in? And once I start to talk about direction, I will now talk about velocity. Now, we want to find the slope here. We will divide it in motion 1, motion 2, motion 3, which goes until here, motion 4, and motion 5. And then keep trying to find out how much that it gives us in velocity versus time. Now, the first thing we're going to do is to find the slope and then present that slope in the velocity versus time graph. Now, let's look at motion 1. What is the, we look at motion 1. What is the slope of motion 1? Now, we have our change in motion, our change in position goes from 0 to -4. But we said that here, our formula of average velocity, we take the final position and subtract the initial position. Now, our final position will be -4, and we subtract the initial position, which is -0. And by -4, I know that you cannot count distance by a negative. You cannot say you moved negative position. What I'm actually saying is that from our point of reference, you moved an opposite direction than the positive that we had agreed on. Now, if you were to say the right is the positive, so from our reference point, that means the person moved to the left. So now that person is at -4 instead of 4. So over the time interval, how long did it take to move from point A to point B. Now our x-axis gives us time, and it shows that we only moved 1 second time interval. Therefore our velocity here will be minus 4 meters per second. Now this negative only tells us that the person moves in opposite direction. So that person moves 4 meters per second in opposite direction. There's no such thing as a speed of minus 4 meters per second, but you can move a velocity of minus 4 meters per second. Velocity is a vector giving us magnitude and direction. Therefore the minus sign says you moved in the negative direction. And now that we understood how to do that one, then we can go faster on the others. So let's present it in our velocity versus time graph. We know that the velocity is minus 4. Therefore we'll come to minus 4 here, but it is for how long? It is for 1 second. So they move minus 4 meters per second for 1 second. Therefore you will see that your velocity versus time graph will be a horizontal line, because the position versus time graph is a straight line. So the motion, the speed is constant throughout the entirety of this line. Therefore we'll only have a constant negative 4 meters per second, which is uniform motion. Now from 1 second to 4 seconds, it moves in a horizontal line. Therefore it doesn't actually change position from negative 4. It stays at negative 4 for 1, 2, 3 more seconds. Therefore it has no speed. We can even calculate the same way we calculated motion 1 and say for motion 2, what is the average velocity? The average velocity is taking the final position, which is minus 4, because our particle it's still at minus 4. Let me just draw it with red to show that our particles moves from there to there to there to there. Now our final position in this motion 2, it is still minus 4, and our initial motion is minus 4. Time has passed by, but our position hasn't changed. So we will subtract minus 4 over time interval. It stayed there for 1, 2, 3 seconds, which is, we can even be more practical so that you see actually what we are doing. It is there at 4 seconds. Subtract the initial time, what time it was there at initial position, which is minus 1. So this will give you 3, and that will give you 4. Minus 4 plus 4, which is 0. So we have 0 meters per second for motion 2. So it is not moving for 3 seconds. How do we present this in our velocity versus time graph, which is this one? It means that from T1 to T4, we have 0 velocity. So our graph will be along the x-axis, and it is a horizontal line because it is uniform motion. It's just that it changes the speed that is moving at between each motion, but each motion 1, motion 2, motion 3 are individually uniform motions. Now from T4, let's see what is the slope of motion 3. We take the final position, which will be we take the final position of motion 3, which will be 0, subtract the initial position, which is minus 4, over time interval. Our final time is 8, our initial time is 4 seconds. So we will have positive 4 over 8 minus 4 is 4. So 4 over 4 is 1 meters per second. So motion 3 moves at 1 meters per second, which is here. So our motion will go up and move at from motion 4, from time 4, t4 until t8, it will be 1 meters per second. Now let's do the other ones quick. For motion 4, our final position is 3, our initial position was 0, our time interval, we are at 11 seconds, subtract the initial time, which was 8 seconds. So we have 3 over 11 minus 8, 3, which is 1 meters per second. So it continues to move at 1 meter per second until time is 11 seconds. Now for motion 5, our final position is 0, subtract initial position, which is 3, over our time was 13 seconds, subtract initial time, which is 11. We have negative 3 over 13 minus 11 is 2. So we have negative 1.5 meters per second. So we will draw it here again and go to negative 1.5, which is here, and draw our velocity versus time graph. Now you start to notice that when we move in the opposite direction, we say our negative shows us opposite direction. Therefore, the slope will be negative. And you know that a slope that goes this way, it is negative, and a slope that goes this way, it is positive. Another thing that you can take from here, that you can deduce from our position versus time graph, is that when a slope is far steeper, you will have a larger speed. So when a slope is steep slope translates to faster speed. So if the slope is steep, we'll have faster slope, and horizontal slope mean no motion, constant speed, therefore which is 0, never mind. So, and that's how you find a corresponding velocity versus time graph. Now, the examples that we have did so far, we knew that we were talking about position versus time, but we didn't know exactly what axis we were working with. So can we actually find an equation for the uniform motion for general axis? So in this case, we'll call this axis the S axis. Therefore, our position will be denoted by S, given in meters, and our time will be given in seconds. Now we are finding the motion, the equation for uniform motion for general axis. It's just finding a general formula. So we are going to find this by saying, okay, let's draw a straight line. We know that uniform motion will be a straight line, will be a nice linear line. It doesn't matter whether that line is negative or that line is positive. Now we know that at the beginning here, at the beginning of your motion, you will have an initial time and you will have a denoted initial position. Now I'm denoting them position as S because we are dealing with the general axis, which are the S axis. Now after a certain amount of time, you will have final time, and we'll find out how long it took you to move there, and then we'll have your final position. Now we just said from earlier on in the video that to find the velocity, we have to calculate the slope, which in this case it will be change in s over change in time interval. Now let's write that down so that we can see how can we represent it by an equation. So to represent it by equation, we'll say to find the velocity, we need to find the change in s over a time interval. Now the change in x is presented by s final, which is our final position, subtracted by s initial, which is our initial position. Our time is given by tf subtract ti, tf minus ti, which is our time interval. Now the numerator gives us a change in position in our general axis, and our denominator gives us our time interval in seconds, position in meters. Now we can rearrange this formula so that we can calculate our final position if we wanted to. Now this is sufficient, but what if we wanted to find out our final motion? What we can do now is make SF the subject of the formula. To make it the subject of the formula, I am going to multiply the time interval with the velocity, and I'm going to return it to be just delta t. So delta t multiplied by velocity is equal to SF minus SI. Now we wanted to make SF the subject of the formula, so we'll have SF equal to delta t times V. We move S and transpose it to the other side, it will be positive SI. Now for people who already know the equations of motion, you will now start to notice which formula is this one. So I'm going to rearrange it and say SF is equal to SI plus V delta t. Now this is called an equation of motion. It will be our equation number 1 as we go along down the equations. This is how it comes about. There will be more equations of motions that are more complicated. This is the simplest one and my favorite one of all the equations of motion. Now it is an equation of motion, and in this case it shows us the change in position in the general axis for a uniform motion. And now let's make an example to see how it works. Suppose that Karabo leaves Burnley at 8 a.m. Now she's driving to Brighton, which is 400 kilometers away, and she drives at a steady, meaning that it is constant speed of 50 kilometers per hour. While at the same time, Archie leaves Burnley at 9 a.m. This is an hour later from Karabo, and drives at a steady, constant uniform motion at a steady 60 kilometers per hour. So she leaves later, but she's traveling faster, 10 kilometers per hour faster. So the first question is, who gets to Brighton first?